6.3 part 2, more vectors. Alright, so from what we talked about yesterday, we talked about magnitudes of vectors. So what did we say yesterday? What is a unit vector? Vector with magnitude 1. So what we want to do now is talk about how we find a unit vector. If a unit vector in the direction of v we're going to say our vector is not equal to 0, so we're not talking about the 0 vector, we're not talking about a vector with magnitude 0. A unit vector in the direction of v is, and I'm going to call that vector u for unit vector. All we do to find a unit vector is take our vector and divide it by its magnitude. So basically we're dividing out the length. And you'll also see this written as 1 over the magnitude times v. So we're taking our vector and we're dividing the length out of it, basically. So if we have, for example, if we had v is the vector 3, negative 4, and we want a unit vector in the direction of v. So the first thing we need to do is find our magnitude. So the magnitude of v is going to be the square root of 3 squared plus negative 4 squared. And what's that going to be? Hypotenuse of a right triangle with legs of 3 and negative 4? 5. So our magnitude of vector v is 5. So our unit vector is 1/5 times 3, negative 4. And I could also write that as 3/5 negative 4/5. And that's my unit vector. Yes. The unit vector in the direction of v is. So I can move this up here, direction of v. Unit vector in the direction of v is u, for unit vector, is v over the length of v. And if we found the length of this vector, we would find that the magnitude comes out to be 1. So to find a unit vector, divide the vector by its length. So what if the problem asks us for a vector with magnitude 10 in the direction of v? What would I do? We want the magnitude to be 10. Here's a vector of magnitude 1 in the direction of v. So how would I get a vector with magnitude 10 in the direction of v? Yeah. Multiply the unit vector by 10. Here's a unit vector, magnitude 1. If we multiply by 10, we make it 10 times longer. So vector with magnitude 10 in the direction of v is 10 times the unit vector. 10 times 3/5 negative 4/5. The magnitude of this vector is 1, and we multiply that by 10. What if we wanted a vector with magnitude 5 in the opposite direction of v? What would we do then? Multiply it by negative 5. The negative changes the direction, and the 5 gives us the magnitude we want. So anytime a question is asking you about a vector with magnitude something in the same direction as another vector, you find your unit vector and then multiply by whatever magnitude you want. So that's one kind of problem that confuses students, but it's a really easy problem. Find your unit vector and then multiply by whatever magnitude you want that vector to have. If you want it to go the other direction, you multiply it by a negative. That changes the direction. Yes? So that one, the kinds of problems that we'll get here will only be problems like this. So we want, and there is a way of finding that a vector perpendicular to the other vector, but it takes more work than we know how to do yet. Okay? Yes? Yes, because we want to divide. The idea here is we're dividing by the magnitude. We're dividing the magnitude out of the vector, essentially. So if our magnitude is 5 and we divide by 5, then 5 divided by 5 is 1. So we're getting rid of that magnitude by dividing by its magnitude. All right, yes? So our magnitude is 5. We want to get rid of that magnitude. So the magnitude of this vector is 5. We want to divide that 5 out of the vector, essentially. So if we found the magnitude of this, it would be 5. We want to divide by 5 to get the magnitude equal to 1. 5 divided by 5 gives us 1. Okay? So yeah, I would use this, whatever I get after I divide it by 5, to get any other magnitude, because the magnitude of this vector is 1. Okay?
So if we got the second question, would you just put just how it is written right there?
That's fine. Or we could multiply this out. So I could multiply I could reduce this fraction. 10 divided by 5 is 2. So we could say that's 6 comma negative 8. Right? Because when I multiply in 10 divided by 5 is 2, and 2 times 3 is 6, same thing there. So either way would be fine. Yeah.
So you actually have to find the vector, or you just find the magnitude. First one is 5, and then from the magnitude 10, multiply it by 2 is 10.
Yeah. But if it weren't 10 and 5, then it wouldn't be quite as easy to see that relationship. All right. So there we have, that's what we do with unit vectors. Unit vectors are going to be important. So we need to talk about next our standard unit vectors. And if you are taking, or if you have taken physics, this is how you usually see vectors written in science, is with the standard unit vectors. So our standard unit vectors are I hat, and that is the vector 1, 0. So it's vector magnitude 1 in the x direction. And j hat is the vector with magnitude 1 in the y direction. And we draw a picture here. There are axes. What we're talking about with our I hat and j hat are just vectors with magnitude 1 along the x-axis and along the y-axis. So that would be I hat, and that would be j hat. And this just gives us another way of writing vectors. So if we have v, some vector v, in component form is v1, v2, we can also write that as v equals v1 I hat plus v2 j hat. This tells us we go v units in the x direction, and v1 units in the x direction, v2 units in the y direction. And what we call this is a linear combination of I hat and j hat. All right, folks, the technology needs to go away, please. So if our problem, for example, let's do our favorite vector here. If v is the vector 3, -4, and the problem says write as a linear combination, of the standard unit vectors, I hat, j hat. All this is asking us to do is say v equals 3 I hat minus 4 j hat. It's just a different way of writing the vector. It means the same thing. 3 units in the x direction, -4 units in the y direction. And you'll see this, the I hat, j hat notation a little more in science. You'll see the bracket notation a little more in math. All right, questions about our standard unit vector? Standard unit vectors. All right, next we're going to bring back our old friends, trigonometry. And talk about direction angles. So if we draw our vector in standard position, so there are my axes, and here's my vector in standard position. Like we did for angles, we're going to rotate counterclockwise from the positive x-axis. And we're going to call this the terminal point here of our vector, the point x, y. And this is vector v. And for the first part, we're going to say the magnitude of v equals 1. We're going to turn our vector, like we said yesterday, into a little right triangle. So if the magnitude of this vector is 1, if this hypotenuse of this right triangle is 1 unit, what's the x component here? What's the x side of this triangle? What is it? Cosine of theta. And the y component? Sine theta. So if magnitude v equals 1, we can say that v equals cosine theta sine theta. And that's the same as writing cosine theta I hat plus sine theta j hat. So if we have a unit vector in standard position, and we know this angle that we call the direction angle, we say theta is the direction angle. If we know that direction angle, then we can write the component form. Or we can write it as a linear combination of our standard unit vectors. If the magnitude of v is not 1, so we don't have a unit vector. So what we're talking about here is we have a little triangle. We're going to say that V is the vector V1, V2. So there's V. This side of the triangle is V1. This side is V2. Here's my direction angle. I can do the same thing with this triangle, except my magnitude isn't 1. So V1 is going to be the magnitude of V, the length of that hypotenuse, times cosine theta. And V2 is going to be the magnitude of the vector, the length of the hypotenuse, times sine theta. So I can write V equals the magnitude of V times the cosine theta, magnitude of V times sine theta, and as a linear combination of I and j, this would be magnitude of V cosine theta I hat plus the magnitude of V sine theta j hat. And all we're doing here is using our right triangle trigonometry to find these two sides of this little triangle. So if you're in doubt, draw the little triangle. You can always use these two numbers to draw the two sides of a right triangle, and the hypotenuse is the magnitude of your vector, and you can find the lengths of those sides using trigonometry. And if we know V1 and V2, if we know these two sides of our triangle, here's V2. So we know our component form. And here's V1. How would we find our angle from V1 and V2? Inverse tangent. This is the adjacent side. Sorry, this is the opposite side. This is the adjacent side. So tangent theta equals V2 over V1, opposite over adjacent. So theta equals the inverse tangent of V2 over V1. And this lets us find our direction angle if we know the component form of our vector. All right, questions there? So we're just drawing, for this piece, we're thinking of our vector as making little triangles with an angle theta here. All right, so let's look at an example using this idea, and then that's really just about all we need to talk about today. So let's say we want the direction angle of this vector 2i minus j. So first off, what quadrant is this vector pointing into? Which one? Fourth quadrant. This is a fourth quadrant angle. We're going 2 units this direction and 1 unit this direction. So we're down here in the fourth quadrant. So there's my vector, V. And that's 2 and that's negative 1. And we can find this angle in the triangle, right? How do we find that angle in the triangle? Here is the opposite side and here's the adjacent side. Tangent theta equals negative 1/2. So theta equals the inverse tangent of negative 1/2. I plug that in my calculator. Usually with vectors we're in degree mode. So in my calculator, I get theta is about negative 26.57 degrees. Is this angle in standard position? Is this a standard position angle? So what do we need to do to find our standard position angle? Our standard position angle is that. Subtract it from 360. So standard position (360 minus 26.57), and I get about 333.4 degrees. So this would be my angle in standard position. This angle counterclockwise from the x-axis. All right, questions there? So the vast majority of the homework tonight is going to involve the stuff that we just talked about, finding our vector in terms of I and j, talking about the direction angles, writing with sines and cosines. But there are two problems, number 98 and 100, that are what we call static equilibrium problems. So what I want to do is just show you how to set these up, problems, because we do them all exactly the same way. So these problems are all going to have something to do with like a weight hanging from cables. And they're all going to give you either some angles or some way of finding angles. So let's say this is, I'm going to say that's 50 degrees and that angle is 60 degrees, for example. So all of these problems are you're going to set up the same way. They'll all give you the angles or give you some way of finding the angles. It might not be these angles, it might be some other angles, but they're essentially the same. For all of these, since they're not moving, the horizontal components, they'll ask you to find the tension, T1 and T2. They'll ask you to find the tension in these cables. The horizontal components, the x components, have to equal each other. So the weight is not moving side to side. So you set the x components equal to each other. So if the x components don't equal each other, this thing's going to be moving, and that's not what the problem is describing. So the x components have to equal each other. And the y components, it's not moving up or down, so the y components have to add together to equal the weight. So what I do with these kinds of problems is we're going to split this into two triangles. So I'm going to split it like so. These are 90-degree angles. And you don't have to draw them separately, but sometimes it can help you visualize what's going on. So I have one triangle there, and I have one triangle there. That's 50 degrees, and this is one thing we're interested in, and this is 60 degrees, and this is the other tension we're interested in. So from these triangles, how do we find this side of this triangle? This is the adjacent side of adjacent to the angle, so cosine, T1, cosine, 50 degrees. How do we find this side? T2, cosine, 60 degrees. This is the opposite side, so this is going to be, how do we find this side? T1 sine, 50 degrees. And this side, T2 sine 60 degrees. These two are balancing each other out so that the weights don't move side to side. So we say T1 cosine 50 equals T2 cosine 60. And these two have to add together to equal the weight. So T1 sine 50 degrees plus T2 sine 60 degrees equals whatever the weight is. And now we have two equations with two unknowns, T1 and T2. So I could solve one equation for T1, substitute it into the other equation, solve that. So we have a system of equations to solve it. So all of these problems, you're always going to set them up exactly the same way. The x components of the tension have to cancel each other, they have to equal each other, and the y components have to add together to equal the weight. Every single time you set one of these problems up, you set it up this way. Now, depending on the angles they give you, it might not be cosine 50, cosine 60, etc. If they give you a different angle, you would have to use that information to find the missing sides of your triangle. But you're always going to set the problem up the same way. Find the x parts, they have to equal each other. Find the y pieces, they have to add together to equal the weight. So number 98 and 100 are problems like these, like this. Always set them up the same way. You always end up with a system of equations. All right, questions there?